Now, in engineering, you'll find that there are a lot of structures that come with various kinds of supports. Okay? And we need to understand what kind of reactions those supports actually exert. Okay? So these are some of the different kinds of supports you'll see: cable, rope, chain, pin, roller, built-in, cantilever. Right? So the question is what kind of reactions we get from them. So let's look at cable. Cables can only be in tension. Right? You cannot really compress them. If you try to compress them, they'll just deform. So they can only be in tension. So if you have a situation like this where you're trying to pull on something and you draw a free body diagram of this paint bucket, you will have the weight of the paint bucket and you'll have the tension pointing upward, right? Really very simple. So the tension part is easy to understand. Cable, rope, chain, they can only support tensile forces. Example, if you have a sign, right, connected by two cables, we know cables can only apply the tension. So what you have to do is you just have to draw the tension, and in this case they're drawn in the tangent direction, and you have the weight. That's it, right? And notice how I also draw the coordinate system. It's very important. Then we have commonly supported reactions. Now, when you get to 260 and 363, you will deal with these kinds of things pretty much every day, right? So it's important to understand this now. So a lot of trusses and the bridges, they actually have this kind of basic support structure, and it's called a simply supported structure, right? What do you have in the simply supported structure? You have a beam, right? And there would be typically repetition of this on a truss or a bridge. You have a beam. On one end, you have what is known as a pin joint. A pin joint is basically no different from a pivot or a hinge, like what you have in your doors over here, okay? The technical term we use is pin joint, but it's nothing but a hinge, right? What is a pin joint? Pin joint basically allows rotation, right? So if I hold it over here and this thing is freely allowed to rotate about this, that's a pin joint, okay? There is nothing that will prevent it from rotating apart from maybe the friction that you may have at the hinge, right? Otherwise, it's freely rotating, okay? No friction, no torque, no moment that will oppose this motion. But if you try to pull it from here, it's going to keep it here, right? Which means that if you take the pin support away and you draw the free body diagram of this object, there will be forces that will keep it in this direction, right? And that force could be in this plane, either in x direction or y direction, or in both of them. So in general, we say that pin joints can apply two reaction forces, one along x direction, another along y direction. Why both of them? Because we don't know which way the real force is going to be pointing. So we just say we have two components, right? Because if you take this, it can freely rotate about this point, but it cannot get away from that point. Because if you try to pull it, this is going to keep it in this place, right? Then on the other end, you have a roller. So now, see what can happen. As this thing extends, because of maybe thermal expansion or anything like that, this end is free. It is not constrained at one point, right? It's free, which means that as it moves, the roller can allow it to nicely roll, right? It can allow it to nicely roll, which means that at this point, the only force you can have is the one that will be in the direction perpendicular to the tangent. The tangent line is this, so the direction is just a normal reaction. Because in x direction, there is no constraint. It can freely move in the x direction, and there is no constraint for rotation as well. So there's no moment, there is no x direction force, the only force you have is in the y direction. So if I give you something like this and say, hey, draw a free body diagram of this beam, you will draw these two reaction forces, you'll draw this normal reaction, and it'll show the weight. That's it. That's a simply supported object. If I put two pin joints, you'll have two reactions here, you'll have two reactions over here. If I put two rollers, I'll have one reaction over here, I'll have one reaction over here. So depending on what sort of connection you have, you could have different number of unknowns, right? You'll have different number of unknowns. In this case, you have three unknowns. If you have two pin joints, you'll have four unknowns. You have two rollers, you'll have two unknowns, right? This is another example called cantilever. So this is a sort of attachment that you can create if you push something inside, let's say, a plank, or you create a rivet joint. That will be also a cantilever action. And essentially what a cantilever action does is it not only gives you a reaction force in xy direction, but it also prevents rotation, right? So if I take this thing and you really push it through the wall or attach it with a plate which is riveted or screwed or bolted, then it will not allow this rotation to happen, which means if you try to push in this direction, there will be a counterclockwise rotation. There will be a moment in the opposite direction, right? So we say that a cantilever support can provide not only x and y direction forces, but also a counteracting moment. So you have three unknowns with the cantilever support, right? So pin joint, 2 reaction forces, a roller, 1, and with a cantilever now you have 3 unknowns. So if you try to apply a force in this direction, there is a counteracting moment, right? Okay, so that's good.